So let's return to the next section of chapter one from our textbook. So I'm going to share the PowerPoints here and let's pick up where we left off. So in this slide here, um, we're going to start describing matter. So I mentioned previously that matter takes up space, so it has a volume and it also has mass. So there's some quantity of atoms present. So things like your textbook, if you had a physical textbook, your desk, your chair, and even you are composed of matter. So all of our cells. Um, so, depending on the state of matter, so this means is something called a solid? Is it a liquid? Is it a gas? That's our physical state, our physical form. Composition, that is referring to is it only one element? Is it two elements bonded together to form an ionic compound? Is it a molecular compound? Because it's only nonmetals bonded to one another. So, the composition, the components, elements compounds? Is it a mixture of these types of things? So that's what we're going to talk about here, this chapter, or this part of this chapter. So again, we can classify based on phase of matter as solid, liquid, or gas. And then each of these different phases exhibit different properties. So generally, we can think of water. So in its liquid form, we can drink it. In its solid form, it's ice. And it actually floats on its liquid form, which is unique to water. But when we talk about molecular geometry, it will make sense why solid water floats on liquid water, whereas most other matter, a solid phase would sink in its liquid phase because molecules or atoms are packed tighter together in solids than they are liquids usually. And liquids can move freely. Gases, these types of molecules have the most energy and they're moving around freely. So we see different properties on based on different phases. Usually temperature is the factor that contributes to phase change. So if we increase temperature, usually we can go from solid to liquid to gas phase in that order. Depending on changes in temperature, we may go back and forth between those phases, but we still have the same matter. Just a phase change would not be any type of chemical change to the compound or the matter. So again, we can see here a distribution using these little green balls here of solid matter. Our atoms are packed tight together. They're nice ordered and structured in our solid phase of matter here. Then we get to liquid matter in the middle of this middle Erlenmeyer here, and we see our green liquid now. They're able to kind of flow past one another, these atoms or these molecules. And then our gaseous matter. Again, it could be elemental matter or could be compounds in gaseous phase in this Erlenmeyer. But notice it fills the whole flask. So we can see different properties taking place before our eyes here or being displayed. So solid matter does not take the shape of its container, whereas liquid matter will fall to the bottom of the container that it's in and it will create this surface. Gaseous matter will expand to fill whatever container it is in. So different properties. We can see what I just described here. Even though these atoms and solid matter are tightly packed together, they're still vibrating. They are still, they have some kind of motion involved with their bonds. But they're not moving past one another. And that's what we would see with our liquid phase. When we get there, that molecules can move past one another. But we have both a fixed volume and a rigid shape. So things like ice, aluminum. So when you wrap your food items with aluminum foil. Diamond, these are all solid forms. We can have a crystalline type of structure where we see these long range repeating patterns. So these are all carbon atoms here. This is one form of solid carbon where we have this structured, crystalline, regular, three-dimensional pattern. And then we can see other types of solids that are more amorphous. where they don't have this type of structured pattern. We don't see this represented molecularly here in any image, but glass and plastic polymers that are called plastics. These are examples of amorphous solids where there's no regular repeating pattern, but they still have the same phase. Another um, another form of solid carbon was graphite. If you saw the intro video, you would have seen another form of solid carbon. So these are different allotropes of carbon when we talk about graphite and diamond. And then we have, again, different structures such as amorphous, where there's no pattern, such as with the crystalline solids. So that brings us to liquid matter, where now our atoms or our molecules, they're able to move past one another. But they're still fairly close, but able to freely move past one another. So molecules of water, ethanol, such as drinking alcohol is ethanol, and then there's isopropyl alcohol, rubbing alcohol. Either of those are molecular in structure, but in liquid phase at, a certain temperature, we would see these molecules flowing past one another. Gasoline, we'll learn that's a mixture of different hydrocarbons, different compounds in solution. So in liquid phase, molecules move past one another. In gaseous matter and gaseous phase here, these molecules or atoms, say like a helium atom, is all by itself. But in gaseous form, these have the highest energy compared to other phases of liquid or solid of the same atomic type. They're moving past each other a lot faster because they have more energy. They will take the shape of their container. They have a lot of space between them as a result. So we can see this comparison of solid matter over here on the left, which is not compressible, versus over here, we'll box this in, where we can see these gas molecules, we can squish them tighter together. That's called compression or compressibility. So gases have this quality, whereas liquids and solids we usually say are non-compressible forms of matter. So what are the components we can further elaborate on here? We talked about matter according to its composition. We defined an element would be a single type of atom. Compounds, this is where we have two or more atom types bonded together. And then mixtures, this would be where we have elements, compounds, more than one element, more than one compound, not chemically reacting with one another, but in the same place. So we have a variety of elements, compounds, what have you, that form mixtures. And then we can further find subsets of those mixtures to be based on appearance, whether they all look the same or they look a little different. So let's break down matter here a little bit more. So we're going to start at the top here. And we ask ourselves this first question regarding matter. Does it have variable composition? So what does that mean? If I took a sample on the left over here, and then I took a sample on the right, and I analyzed them, do they look exactly the same? If the answer is no to this question, is there variable composition? So the samples look the same, then I know I have a pure substance. Right, so won't let me remove that, but then I have a pure substance, right? If there's not variability in my composition. But if I say, yes, there is some variability, if the sample over here looks a little different than the sample I took of the same matter, then it must be a mixture of different elements, compounds, what have you. So again, it doesn't have variable composition. If we go over here to pure substance, we can then pause here and say, okay, if I can separate this into simpler substances, then yes, then I have a compound. So for example, if I have water, it's H and O. There's H2O is the molecular formula. So there's two hydrogens, one oxygen. Through electrolysis, I could break down this compound, this molecule rather, and break it into hydrogen and oxygen. I could separate it further. So that's the question that we're asked here. Is this separable into simpler substances? So if the answer is yes, right? Then we have a compound. So an example of that could be H2O, water. But if the answer is no, say we had just H2 gas, just hydrogen gas, then we would say we have an element. In this case, we see the blimp here. Helium tends to be just singular atoms. They do not form bonds with other helium atoms, and we would just have these single atoms in elemental form. But H2, hydrogen gas rather, takes on a diatomic molecular form in its elemental state, but both of which are considered pure substances and elemental versus our pure substances that contain two or more elements. So that's on the pure substance side. But if our matter does have that variable composition, we would say yes to this question. Remember, that's our starting question when we think about matter. Now, is it uniform throughout? So now that we know that we have a mixture, that there is some variability in our composition, we further, probe into this and say, how does it look? Does it look the same? Does it look homogeneous? Like this tea with sugar dissolved in it? Is there any visual starting point for the water molecules, the whatever caffeine molecules, and the sugar molecules? Can we really see where they start and end? So no, I cannot tell with my with just my eyes where these different molecules end or begin. So I would say that tea with sugar dissolved would be a homogeneous mixture versus wet sand over here in this image. If we had, a glass or a beaker with some sand and water in it, we would see a distinct separation. Well, we do have a mixture. It would be what's called a heterogeneous mixture, where we can visually see differences. At times, you can actually separate the molecules quite easily. And those are signs or indications that you have a heterogeneous mixture versus where you can't tell where one molecule begins and ends. That's more of a homogeneous mixture. So, again, our first division of matter is it a pure substance or is it a mixture? And then we break down our pure substances, only one type of element versus more, two or more would be a compound. So we have elements and compounds are both pure substances or can be. And then if we put two or more of those together, we get a mixture. So we could have two pure substances that form a mixture. And then, depending on phases of matter, things of that nature, we may see a heterogeneous or physical distinction, or where we can't see that distinction, a homogeneous mixture. So again, two types of pure substances, element or compound, can't be broken down into simpler substances unless you do chemical types of means. Um, Here's a further definition of what an element is, right? It cannot be broken down chemically. Two or more elements fixed in a definite proportion. I forgot to mention that. That's what makes the compounds different from each other. We could have CO, which is carbon monoxide, versus CO2, carbon dioxide. All right, so I know we've been talking for a while here. So let's see, we talked about mixtures. So if something does not get dispersed uniformly, we can think of that as a heterogeneous mixture. There's more clumps of, chocolate chips in our cookie on the left side than the right side. That's a heterogeneous mixture. We could actually pick apart the different components versus homogeneous. That's where we see this uniform distribution of something dissolved in something else. So here's some examples of a heterogeneous mixture. We have salt and sand mixed together, two solids that we could, if we had enough time, pick apart salt crystals from sand crystals. Um, and then our homogeneous mixture. Usually we cannot pick this apart by hand, but there may be ways to separate, say, if we had sugar dissolved or salt dissolved in water. If we evaporated the water, we could collect that, separate the solid salt or sugar crystals. So there are ways to separate mixtures versus pure substances. So keep that in mind. And that brings us to this final type of question here, where we can see how pure substances are indicated by these graphical representations of these circles and squares here. So in image one, we see a red square bonded to a blue circle. So each of these compounds, right, we're indicating two different elements here. In image B here, we see those two elements, but they're not bonded together. They're kind of separated, or they're separate entities, but they're mixed together. So there's kind of a uniform distribution. So we could look at this and say this is probably a homogeneous mixture. Um, Answer C here, we see a distinct separation, distinct layering. So this could maybe be a heterogeneous mixture. There's some kind of separation. Maybe they're two liquids like oil and water. But A here, this could represent a pure substance because it is all the same thing. It's a representation of all the same compound with, the red square bonded to the blue circle. So we'll pick up on how to separate mixtures in the next video.